Thank you. Well, thanks for coming. I know it's right in the middle of the workshop. We're all a bit tired of attending talks, so in spite of the 67 slides, I'll try to be fast, to finish a bit early. But there's natural break sort of in the middle of the presentation, so I guess we'll just take a break at that point. I'm going to talk about multi-object dynamical system or multi-target tracking for more applied people. And so it's a topic I've been working on for a number of years, about 9 years actually. So I started as a research engineer in a French company that was called DCNS at the time, it's now called Naval Group. So they built ships for the French Navy. And of course they have multi-target problems with all the data they receive from the radars, the sonars, any type of sensors that they have. And so, I found the topic interesting, so decided to do a PhD on the topic. So that's another 3 years, and since then, actually, so I spent 2 years here in Singapore, and in particular with AJ and Sumit, we've looked at more sort of theoretical aspects of it. And so today, I'm going to try to convince you that it's a very interesting inference problem. It's complicated, but in a sense, because it's complicated, if you can do inference on it with some method, then you're pretty sure that your method is quite robust. So I find it's a very good test to understand if something works and scales well, or if it doesn't. Okay, so the outline. So I'll give some very general overview, some pictures, some videos. I mean, it's relatively simple to understand what we're talking about, but just to have an idea about what the sort of applications that are interested in multi-target tracking, and also the sort of techniques, the sort of naive techniques you could try to solve the problem, and we'll see why they don't work or why they don't always work. And then I'll move to the sort of point process formulation. And so I'll give a lot more details here. I think it's interesting. You can really basically put the problem as an inference problem, Bayesian inference problem for point processes, at least in some cases. I'll also talk about some alternatives to that. And actually, I'll finish with something that's a bit more exotic, I would say. And so I'll keep the motivation for later. And actually, in a sense, the beginning of the talk is a motivation for the last section. So this we'll do after the break. All right. So, well, there's multi-target tracking problems in really a lot of different applications. So these actually all things I've worked on during my PhD. So here we have some microscopy problems. So actually, this is the image of a live cell. And so it's the surface of the cell. And so the people want to understand how the proteins, they sort of behave at the surface of the cell. And actually, because it's a live cell and you can't put too much light on the live cell, otherwise you kill it. So it's very typically a low signal to noise ratio. And so biologists often they do things by hand. They have a lot of manpower and a lot of time. But here I mean, I don't have the video here, but it would be very hard to do the tracking by hand. So even in this case, even if you have a lot of people and a lot of time, you can't do it. So here it's very important. Of course, it's an important application. So there's also, of course, a lot of defense applications. Maybe that's one of the most obvious. So here I have an example with some heavy traffic lane for ships. And maybe that's a restricted area where we only want some authorized ships to go in. Yes, that's that's in the Netherlands, yeah. It's completely at random, I have to say. So for instance, here, not only we want to follow things that are going around, but maybe we want also something on top. We want to say, oh, is there something going in this area, right? And that's pretty simple. But we also have, maybe there's like a lot of things in the water, fish, everything. So you also want to classify. So there's for instance, we can do multi-target tracking with classification, and that's something that we can do sort of in the Bayesian spirit altogether. So it's not only just tracking. There's other potential tasks that are associated to it. Space debris tracking, I think this is getting quite well known. There's a huge amount of space debris that are going around Earth, and so it's a very difficult problem because there's a lot of them, and that's the concern about it. And it's an increasing number, and it's very hard to observe them very well. If you have like one telescope, for instance, at one place, you only see a very few of them. But I'll talk a bit more about this. And so here's, yet another example. For instance, this is a microfluidic device, and people want to check that things are well sorted, for instance, depending on the size. And so we can automate this. And instead of what they're doing at the moment is looking for hours at videos and checking that everything's fine, you can do this automatically. So to be a bit more, bit more general, so we have a problem where we have basically a certain number of HMM. You can think about it. You can as single object, certain number of objects that are evolve in time according to some dynamic that we can model. But there's also on top of this a birth-death process. There's new objects that appear, old objects that disappear. So the state, if you want to put everything together in one big state, this state is going to change in size randomly. And on top of this, we don't observe only what we want. We have, I started by the end. We have a lot of false positives, so just random observations that come from some kind of background noise. If you're on a ship, there could be waves, there could be things. If you have a camera, just trees moving around, creating a lot of those false positives. And even when you're actually observing something or trying to observe something that might fail, so you also have false negatives. You don't always see everything you want to see. And so all this, I would say, could be okay if we knew what we're observing when we observe it, but the main issue is what we call data association. So basically, we have a certain number of objects and we don't know that number, or we don't know for sure. And then we receive a random number of observations, and we also have to match them. And so that's very combinatorial, of course. And that's one of the main problems, sort of going around this combinatorial aspect of the problem. All right, so as I was saying, so that's Earth. Actually, you can't see it, but right in the middle. And so that's real data. So a lot of debris, or so this, depending on the color code, I can't remember, but either things that we know or things that we don't know. And so a lot of debris, even not only the debris, a lot of things to follow in there. So, and typically, so for instance, okay, so here's like some simulations we have. So it's only just over 100 objects, but that's already a difficult problem. And so, for instance, here we have one, actually it's a radar in Alaska and another one in Texas, and trying to, so the objective here is to, of course, follow all the objects. And I'll play it again. So you could argue, well, we know very well the dynamics of objects in space because there's a little perturbation. But this is, so in a sense, it makes it easy. Yes, we can predict very well. But at the same time, we don't observe them very often. So it's, and we have this typical problem where the variance would be huge at the moment when you observe it. And actually, radars, and in particular telescope, are extremely accurate. So then you have like almost point-away observation, and you of course highly nonlinear dynamics. So that's typically the sort of cases where even just actually filtering is tricky. But on top of this, we have to sort this data association problem. So that's just one example. Here, that's also real data actually. So that's the UK. So we've sort of far of this. So here is all accumulated. That's why you see these sort of trajectories. So you could argue, well, I see there's one track here, one track here. Yes, that's the easy part. Like for instance here, because of the shores or because of some objects that are around, it would be a lot more difficult to make sure. For instance, here if we have a ship, if there's a missile coming here, you're going to have like 1, 2 observations. That's it. So try to find this. And so here is just again another example. So to show that there's a lot of the assumptions we make usually they don't hold, and it's sort of important to take that into account. So here we've typically, that's simulated data, that's a radar, and a bit like pixels for a camera, here we have this sort of small squarish shapes, and so this is the resolution cells of the radar. So the object basically, although that's a trajectory, here is sort of represented as pointwise, but in practice it has some extent. And so if the resolution is very high, basically you get something that's sort of Gaussian, and here you're going to have issues just modeling this as usual. But for instance, if the resolution cells are very big compared to the extent of the object, we have something that's very unusual, I would say. And so, for instance, here, as long as the object is sort of in the middle of that cell, we're only going to get, we only know that it's within this cell, and we don't know anything else. So for instance, so I also have a video just to give some up. Right. So you see it's sort of, you observe for some time in one cell, and suddenly you jump to the next cell. And so this is quite highly nonlinear. You need to take this into account. So here, actually, I made my life simple. I assume that two cannot be at the same time in one cell, but in practice, of course, that can be the case. But that makes the combinatorial just even worse. So I would say with cameras, we don't really have the problem. Usually, objects are really big compared to pixel resolution. So at least for cameras, sort of cameras we use, we sort of used to. But here, with a radar, that's very typical, actually, that the cell is, especially far away, the cell would be pretty big compared to the size of the object. OK. Up. Video. Right, I just come back to this case. So here, for instance, again, we have, so this is a classification problem. Actually, in this paper, we considered so MIMO sonar, so it's multiple input, multiple output. So for instance, you have some receivers here and some transmitters here. You get observations, and so you try to do this classification problem. So if you have a zone to defend here, and you don't want anything to go in it. But when you say anything, you mean any ship. Of course, if you have fish, for instance, that's the green stuff. You have some people dumping washing machines in the harbor, give observations. So this is sort of like just classifications based on dynamic. And you're OK with a fish in your restricted area, but anything that's more like constant velocity sort of model, within that area, you're not happy with. So for instance, here, so this is just the observations. And the black dots are the false alarms, the false positives. And this is the sort of results if you apply multi-target tracking. So here you can sort of raise an alarm saying, oh, there's something that looks sort of man-made that's going straight line, more or less, that's getting into the zone. OK. Of course, you can have some parameter estimation problem, this as sort of usual. But this, I like to show it because it took me a lot of time, especially making the paper planes. So here we're trying to, with two cameras. So cameras, of course, you don't have, when you measure, you don't have distance. You only know the angle, right? And so, but as usual, you just put one camera here, one camera there. You have no idea where they are, even with respect to each other. So the objective here is to just throw some paper planes and try to learn where are the cameras based on that. And so, last video, well, last, yeah, OK, last. OK, well, I skip a bit because that's the video that goes with the. So, well, OK, it's not too bad. So we have this sort of. So actually, this is a bit. I would say it's a bit naive. The way we did it is quite a while ago, but it's just to give an idea of the sort of challenges. So this is the parameter space on top. 6-dimensional. And so here we're presenting the two projections of the sort of position of the camera, and that's the sort of the field of view that's drawn here. And so this, basically you fix one camera, you say, well, that's the origin of my coordinates, and then you try to learn what's the position of the other camera. So 3 angles, 3 positions. And so here we're doing, for each of those particles, we basically running some Bayesian inference for multi-objects, and getting the marginal likelihoods, and sort of learning if the position of the camera is likely or not, depending on if the trajectories make sense and things like this. So it's real data, but we can check that. Actually, I checked. So here we converge. I mean, it's static, so we're staying there. And the lecture theater is about 15 meters deep, so it's not too bad. But this is a really hard problem. So I'm sure there's again, this was quite naive, just to give an idea. All right. Okay, so getting a bit more technical now. Let's say finally, probably. Okay, so for each single object, as I mentioned earlier, we can just think we have a HMM. So I'm not going to write a diagram and everything, because I think we've seen it quite a few times. With some Markov kernel. So the state space, as I write RD, D equal 4 is very typical. You just position velocity in 2D. But you can go a lot higher than this if you're trying to estimate the shape. For real problems, you're actually in 3D, so you have D equals 6 already. So not too big, of course, but that's, potentially that's relatively big, and that's only one object. Okay, so actually initial distribution, you can forget about mu because I think I don't need it. And we have some likelihood again. Sensors observe really a lot of different things depending on the sensor. So, but yeah, D prime is less than D very usually. All right. So we'll make some assumptions that are strong, because otherwise it's really a nightmare. If you're very patient, you can remove those assumptions and try to do something. Of course, the combinatorial is very bad if you, for instance, if you assume there are actual interactions between objects. Even if you just start with pairwise interactions, if you have a lot of objects and you're trying to see all the sort of subset of the sort of binary partitions of your number of objects, that's going to go very high. So in this talk, I assume there's just no interactions. The dynamics are completely independent. The observation of each object is independent. The false positive, the ID, and themselves independent of all objects. Basically, everything is dependent of everything. Birth depth also doesn't depend on anything else. And that's already tricky, right? So, let's take a very, very simple case. I like to take, this is just a 1D example. The state space is just 1D. We measure the position. Let's say think of this as position. This is not very realistic. It's just for the, and well, let's say even we know the two targets. So if you know how to do filtering for those objects, let's say everything is linear Gaussian, you just run some Kalman filters, and so you could say, well, I'm just going to. Going a bit too fast. So we have some observations from those. It's not just observe the position with some noise. The noise not that high here, and we also have those false positives. And so you look at that graph and you're like, well, that's pretty obvious. But if I remove the trajectories and the true observations, that's less obvious, right? Well, at least to me. So as I was saying, you could say, okay, I'll just start. Here we assume actually the initial positions known. And you can run some Kalman filter and take the closest observation in some sense. That's actually what people used to do just after the Kalman published the Kalman filter, they thought, okay, let's do multi-target tracking, but they had really bad computers, so it's not that they were naive, just that's the only thing they could run, and take the closest observation. So the result is actually quite predictable. It starts okay, and then as soon as maybe one object is not detected and they're a bit close, they both go to the same observation. After that, deterministic, they just so we have this phenomenon of track coalescence. That's, I mean, it's a very, very basic approach, but this doesn't work. So I don't have a figure for this, so you can be a little smarter, or if you have a bigger computer, bigger than in the 70s, you can say, okay, I'll just see this problem as a sort of global optimization problem. Yes?
So are you now assuming that you know the number of particles and you also know that they don't disappear?
Yes, here, yes, yeah. Okay. So it's very simple, and even in that simple case, you can't go too simple in terms of solution. So if you do the, so this one is called the nearest neighbor for very good reasons. You can do what people refer to as a global nearest neighbor. So say, okay, I'm going to be to throw a bit more computation to this and try to minimize the sort of distance between all objects and all observations, and select the observations that are closest, but without assigning the same observation to the two objects, right? So this works a lot better. It's a bit harder to show why it's still not such a good idea. So I don't have a figure here. But for basically, in principle, for exactly the same reason as before, if you make a mistake, because you're only propagating basically one possible state for each of your objects, if you make a mistake, then that's it. You can be off for the rest of the scenario. So so it's a bit more robust, but yeah, still not good enough. And so then the sort of next step is to say, okay, I'll just model everything, and I'll just consider all possible hypotheses, all observations with all objects, and just have a sort of more like probabilistic approach on the level of the data association. But of course, it's very combinatorial, and so here I'm being a bit dumb, I say, because of course a lot of those associations, they're completely unlikely, so you can delete them. But so here is just for the previous scenario, I'm just computing all the actual combinatorial. So I'm not actually computing the probabilities or anything. I'm just looking at how many hypotheses. And so even if you know the number of targets and they can't disappear, nothing can appear. After like 50 times step, you have 10 power 40. I mean, this is not very smart. Just to say you have to be careful with these sort of things. And if you allow for targets to appear and disappear, it's even worse, as you could expect. And so this actually, you can run it. It's if you maybe if you apply some more heuristics on top and you say, okay, I'm going to sort of gate. I'm not going to look at observations that are too far, or maybe still rely on some optimization problem, and rather than taking the best, I'll take the sort of 5 or 10 best and give them some probabilities. But you have to use those heuristics. So that's so there are other ways of doing things, and so I'll talk about it later in the point process approach. So just to say something about this sort of problems. So if we're a bit more specific, so there's very usual assumptions. We just consider those false positives, those observations that don't come from our objects. They just ID and and Poisson in number. So you pick how many false positive when you generate. I mean, you pick how many false positive you're going to have, and then you just draw them ID from some uniform distribution. So that's really usual thing. So P var theta is very usually some uniform distribution. So the probability of detection, the probability to see the object if it's actually there, okay, just PD, some number between 0 and 1, hopefully not too close to 0. And if we care about estimating the parameters of these objects, so we have, actually I should have emphasized probably before, sorry. are dynamics and observations. Well, the kernel likelihood depend on some parameter theta. Yes?
Do you assume some particular dynamics here, or not really?
Not really, no. It's because it's very problem dependent. But usually, actually, basically, usually you don't know very much about dynamics. Yes, actually, yes. Space is sort of a counterexample. If you're trying to track people, it's a very unpredictable where they're going, right? So in that case, you just take a Gaussian, a very fat Gaussian, and you hope that's going to work. But yes, for the space application, that's a bit different. I mean, hopefully, because otherwise that would be very hard. So just tag all my parameters. So there's for dynamic and observation, that's my number of targets, probability of detection, rate of the false alarms, false positives, and some parameter of the distribution. I stack everything together. So this is, let's just assume this is a picture. It's not necessary to read it in details, but that's your multi-object likelihood. So things get complicated very quickly because you have to decide, who's detected. Depending on how many you detect, is it likely that the remaining observations are false alarms? Then you have to look at all associations between your objects and your observations. So you have some of the all permutations here, I should have said, and etc. Then you kind of standard, again, false alarms, and that's the likelihood for each object. So that's complicated, but you can still say something if you're interested. If you ask the question, well, do I have some chance to learn those parameters, for instance? And so actually the answer is yes, under assumptions that are, I would say, so I didn't, of course, I mean, when you look at how the likelihood is written, the assumptions are not that simple, but in principle is not that complicated. So actually, I'll come back to the feature information just a little bit later. So in this paper, what we try to do is not only verify sort of consistency like this, but try to make as few assumptions as possible on, for instance, the multi-target likelihood. Right? You don't want to make an assumption here because you it's sort of an overkill. So but if you can deduce the sort of properties that this verifies depending on properties, for instance, on the single object likelihood, that's more interesting. So we managed to do this for for boundedness. It's relatively simple. You still have a bit of work to show that if all those sort of different components behave well, then this guy also behaves well. So basically for this type of result, you also need identifiability. So you basically theta star needs to be a sort of unique maximizer of your likelihood.
Sorry, but can you just went a little bit fast? Can we go back one page?
Sure.
Yeah. So what's x and y again?
Oh. Okay. Yeah, I'll give some details if you want. So x here is just a vector. It's basically a stack of all the states. So here we assume that the number of targets fixed. So basically, x is some vector in kd, right? You have k targets of dimension d.
Those are the true, like the true location?
No. That's just a likelihood, right? So if your targets are at x, then that's the probability. That's just a likelihood, right?
Like what does x stand for?
So here is really just it's just one point in your state space, basically. So you don't know that targets are x, otherwise the problem would be solved. It's just one potential state for all your targets at once.
But y is your data.
And y is the data, yes.
Theta is and here you're trying to find theta or find y?
So, I mean, in the end, we're trying to find theta, and because y is given to us through the observations, right? So here, I guess I should have written a bit more. Here, I mean, once we write this, for the dynamics, I didn't write it because really just everything's independent, so you just take the product of the Markov kernels for each target, and you can just write base rule, right? That's your likelihood. It's complicated. It's just you can write base rule as usual.
Sorry, I just want to clarify one thing also.
Sure.
So all those K objects share the same parameters.
Yes, very good point. Yes. So the theta, yes, theta is in common. So if of course, you could generalize and say, oh, okay, each target has a different theta, but it makes things more complicated. And in the end, we would be interested anyway to stop assuming that the number of targets is fixed, in which case you would have a variable number of thetas, and that's standard sort of approach doesn't apply. That's a bit clear. Oh, so no. So here actually we really care about only the detection. So this is for the false positives. So you say so if you let's say we forgot about data association at some point. You say we just take sigma is identity, let's say, and then you say my first D observations are from true objects, right? And you evaluate the likelihood of this. You say so observation Y1 is from, so you can forget about the R here, let's say, and you say it's from the first object, observation Y2 from the second object, and then the remaining observations after D are all false alarms, right? So you really here, I mean, I didn't put all the details because it just gets complicated, but if you think about the big picture, you're really just assessing the likelihood of some observations Y you've received, given some state, x, and of course, in the end, you'll be interested in integrating over x with respect to some prior or something like this, right? So in this sense, it's really just a normal likelihood. It's just this expression is complicated.
So you have a total capital K object?
So, sorry?
Capital K, what is capital K?
Yes, it's total number of objects. So for instance, here we say this sort of vector D, binary vector, says, for instance, maybe first target not detected, second target detected, etc., etc., etc. So, and you decide for all K targets, right? So, but I won't use this too much. So, I mean, I hope it's clear enough. But it's really just to say things can get messy, but we can still say things, right? And that's just a normal likelihood. Yes. So, for the identifiability, actually, in the end, we had to assume the identifiability of the whole parameter because we actually didn't manage, in some special cases, if you have only one target or if you have no false positives or things like this, you can deduce identifiability of the theta bolds from the identifiability of the different component parameters. But actually, in general, it's either hard to prove or it's not true. We're unsure at this point. But so, unfortunately, we had to assume that the both theta is identifiable. So we couldn't deduce so much that property from property of single objects and of the different components. But so what's interesting here, this in a sense you could say, well, it's not very surprising, but actually this either. But so we have this asymptotic normality also. The assumptions are just technical. It's not really hard to verify. And so, but what's interesting here is we have this Fisher information matrix. And so people who, practitioners, they have a lot of ideas from solving a lot of problems, so how much you can learn about things. About the different parameters in different situations. They just sort of know it intuitively. But we're interested here in trying to understand how these things behave. And so depending on scenarios, do you have a chance to learn your parameter or is it going to be difficult, right? So this is just a slightly generalized definition of the Fisher information matrix, but in itself is not it would be the same if you had a Markov, just basic Markov chain, right? Basic HMM. So now I'll just show pictures. So for instance, in a sense, that's very obvious, but we could verify it using the Fisher information matrix. I mean, of course, you can develop this, but it's going to be complicated. So for instance, if you only say, OK, there's only one object, it's static, and a thing just detected all the time, but there's a lot of false alarms, potentially a lot of false alarms. So, or false positives, sorry. The two are just synonymous. So then you wonder, what's the loss of information? So here is a relative loss, which just basically the loss divided by the Fisher information itself just to normalize things. So it's a loss between 0 and 1. And so of course, that's quite natural. But if your false alarm is distributed on a very large interval, let's say your target is right in the middle of at zero with variance 1. So of course, if it's uniform over a large interval, you have to put a lot of false alarms before starting to lose some information about your parameters. If you reduce this interval, then you lose more and more. Pretty natural. And the worst case actually is the Gaussian case is when of course when the false alarm is distributed just like the target. That's the worst case. You basically lose. I mean, as soon as the number of false alarms increases a bit, you basically lose everything. You can't tell the parameters anymore. So that's a very sort of basic example, but it's things that have not been looked at. So, and I find it interesting to sort of apply standard results we have in statistics and see if it makes sense, see what we can say about those multi-target tracking problems. So maybe a bit more interesting. So now we have 5 static objects with no false alarms, and we see them all the time. But now we have 5 objects, and so here tau is so again we assume the distribution is just Gaussian variance 1, and tau is the distance between them. So basically the first object, let's say, is going to be at 0, then the next one, if tau equals 1, the next one is at mean 1, etc., etc., etc. So in this case, so you would expect that you lose more and more. If they're far, then you don't lose anything. You sort of can tell which observation come from which object and just learn the parameters. If they're getting close, it's getting harder. So here, yellow means the relative loss is higher. But as they get closer, actually, it doesn't matter anymore, basically, which object is where. And so when the separation is 0, they're all superimposed, and you actually just learn the parameters as well as if there's only one object, of course. But I think that's interesting. And so that's also very natural. So here the object moves, and there's no false alarms, but we don't see it all the time. Probability of detection is different from, or in general, different from 0. And so now the loss, basically the loss is linear. Of course, if you don't see the target at all, then you can't learn the parameters. And if you see it all the time, you just learn it as if it was not, if there's not disruption, because there's actually none. And the way you lose it is just linear in time. So all these, I mean, if you do a bit of multi-target tracking, this is going to be very obvious. But no one has looked at it from sort of trying to get the equations. And it's actually not easy, so it's probably the reason. But you can say something, and I think it's interesting to see how those concepts, they sort of apply to a more complicated case like this. So now I'll sort of make the problem a bit harder, and I also assume that the targets can disappear with some probability of survival, PS, between 0 and 1. So just RAD, every time step, you have a probability PS of remaining sort of within the area, or probability 1 minus PS to just disappear. And so we also have birth, and we just assume birth is RAD, and we know the distribution. So you could say, well, this sort of problems is sort of natural to solve it with trying to use MCMC for the data association. So you you just sort of explore all possible connections between observations and targets. And so this has been done, but actually it's, I'm not going to give a lot of details because it's, again, it gets complicated, but the trick here is to design the moves in your MCMC. That's not obvious. If you just do something very naive, the space is huge, it's huge discrete space. So you sort of have to use your knowledge how things behave to design moves. And so you can, these techniques can be either very efficient or you could just, they might not just work at all if of course if the moves are not appropriate. Because again, the space is huge. So you could really get stuck somewhere. And so so this here is just the data association, so just the connections between observations and objects. And Sumit also did this paper where he also tries to learn the state. So this is in general transdimensional, and so you have to use some particle, some PMCMC here. But so just to it's quite natural again, but so this is actually is not the method you've seen, but it's similar type of method, and it's so it's quite natural. You see basically don't mind the change in colors. Basically, the algorithm is trying to see what makes sense in. So here maybe it's missing this, and so you can implement move like trying to extend your trajectories and look for observations that are nearby one way or the other. You have to try to swap. Maybe you have trajectories that have the right beginning, not the right end, and so that's sort of the problem. If you do it a bit brute force, you might have a lot of moves because there's a lot of possible configurations how this could go wrong. And I mean, of course, you need to make sure everything's reversible. So it's one way to solve it. I don't think it's been used so much until now because a lot of people in practice, they actually like recursive methods because a lot of, I mean, if you're on the ship and you want to survey the area, you just needs to keep running, right? So of course this is batch. So what people say refer to as batch. So you have a fixed time horizon here, and those are just the trajectories, and you try to understand how it works. So this could be useful, for instance, in biology applications because even if you spend time exploring the space of the possible data association, you have just one data set with a fixed time, but you really want to understand potentially a complex phenomenon there. So I think that's one of the areas where this could be very useful. Okay, sorry. No, actually, yeah. So of course here then you can just add parameter estimation if you're interested, and that's usually that wouldn't be the that would be the easy bit. I mean, because it's a lot more standard. Yes?
So just to get an idea of how these things run, so you typically have some sort of Gibbs sampler, and then you Gibbs over the association, and then the parameters, and then the state space model?
Yes, yeah, typically, yes. So in this paper, actually, they don't, if I remember, they don't really look at parameter estimation. So you just have the sort of metropolis testing, basic metropolis testing, but really the key is how you design your moves. If you just pick one observation at random and then pick another observation at random and try to create a track this way, you'll never manage, right? So it's so you sort of have to be smart, but you want to keep it simple, not have too many moves, and still be able to cover your the whole data association, right? For the MCMC to converge somewhere.
So it's like a very high dimension of association because every observation you have to associate the
Yes, yeah, it's very high dimensional. That's and you don't have, I mean, there's no natural metric. It's just a discrete space that doesn't have a lot of properties that are nice to explore. So you, really the only way, and just naive doesn't work really. I mean, literally, you could run for years and probably get lost. So it's, yeah, really in designing smart moves, that's the trick.
And they seem to have some dynamics, these like close to linear.
Yes, so of course, in the example I gave, yes, the dynamic of each object would just be, for instance, a linear Gaussian on, so it's position velocity, so we call those models like nearly constant velocity models. But for instance, in other applications, they might not be linear at all, right? So that's why you have to be careful with using these sort of things. The dynamics can change dramatically between applications. So of course you can use the dynamics, but for instance, if you try to look for straight lines, but yeah, that work in one application and completely fail in another application. It has to like take into account all the modeling you have on the objects. Okay, so until now, I didn't get really much into the details because you should thank me, the details are pretty bad. But there's some like sort of, I think, more appropriate way of addressing the problem, at least for some applications, that's based on point processes. And so I've been working mostly on this actually during my thesis. So it's nice because it's very natural to model birth and death with point processes. It's basically it's meant for things that change in size, right? So that's nice. There's been a lot of research on point processes. So we can use a lot of results. We don't have to build everything from scratch. But there's, at least in its basic form, you lose something. You can't tell. Here I say you lose distinguishability. So basically, at one time step, you say, oh, this. Maybe you have some inference that tells you, oh, there's an object here, and you want to know, oh, where was it before? That's actually a hard question because you don't distinguish objects. You're just interested in the sort of the population as a whole, and at least in general, we lose, for instance, the ability to do classification because you can't say, oh, in particular that object, what happened to it, how is it behaving? No, everything is mixed together. It makes it simple, but it's something you lose, and in some applications it can be a problem. So, so now I just assume all the parameters are known. So we have some point process, so that's for the state, xn. So here, k now is a random variable. So in one realization, you have, for instance, little k objects at different positions. And so here we don't really have to assume what point process people call simplicity. So we don't have to assume that all points in the process are different locations. But for the observation, so now the observation is also a point process. You receive a sort of random sort of collection of observations at every time step. So let's say here observation at time step n, and so as I was saying, it's again a point process. But here we do assume it's simple because anyway, when you have a camera or radar, usually you don't know if there's two objects that are very close together and you can't distinguish them, you don't know that. So they'll just tell you there's something here, but it wouldn't tell you how many. So simplicity here is fine. It's not a problem. And again, the birth is another point process that's independent from the states one. So the first. Well, if you see that the point process formulation is nice for the problem at hand, the sort of first thing you do with point process is look at the first moment. So the first moment here, I'll alternate. Sometimes I'll use it as density, sometimes as a measure. But if you integrate it over some subset B, it tells you how many objects you expect to be there. So it's a function of space. It's not like for real random variables. Here, the first moment is a function of space that tells you how many points you expect, how many objects you expect there. And that's what we want to know, so we're quite happy with this. The first moment has a lot of nice properties. So if we apply our dynamics, for instance, to a point process x prime, and we're interested in the result of that, you don't need to work with the point process themselves or with the full distribution. So by full distribution, I mean for instance, assuming there's one point, what's the distribution? Assuming there's 2 points, what's the distribution, etc. That's the full distribution of sort of product space of the point process. Here we don't need to know that. We can just apply this to the first moment, and you can quite easily prove that you just need to sort of apply the dynamics to the first moment of x prime, and you get the first moment of x. So that's nice. That means it's sort of feasible to apply it to a dynamic problem, right? Because you can do prediction basically. It's a sort of Chapman-Goldorff equation, but here you don't have a probability measure. You don't have a probability density. You have a first moment, but it works just the same. And also, if 2 point processes are independent, the first moment of the sum of the 2 point processes, so we just mix up the points together. If we sum those things, this is just the sum of the first moment. So that's very nice too. So I'll just yes.
So gamma is the first moment, so it's not a density? Or?
It's a density, but it's not a probability density. It doesn't integrate to 1. It integrates to the number of objects you expect. Right. So that's when the shortcut density for probability density can be a problem, because in this case it's a density that is not a probability density, right?
There's no restriction on F?
No. Well, I mean, none that matters, right? Like, I mean, basically no unusual assumptions on F here.
No conjugate relationships?
No. That's a very general. So I'll just write a few things on the board. So just also to show you that this is, for instance, the relation 2 is very easy to prove, and the sort of tools I introduced, they'll be useful for later. So this is sort of basic example of how to do that. So I'll write again. We have a point process to capital K delta xi, right? And so one way to prove these things that I think is by far the simplest way is to use the equivalent of probability generating functions. So, but for point processes. So it is a nice way, I think, to sort of deduce it. If you look at the characteristic functional. So I'm not going to define it. I'm just going to write the expression. So you just take the expectation with respect to your point process. Okay. Take expectations, and well, it's sort of general way to define the characteristic functional. So I'll put hat. You understand, because I'll deduce other forms from there. X, and so here I'll be a bit abstract on purpose, because as I was saying, this you'll see for basically random measures, any form of random measure. You can write a characteristic functional like this. So this is the complex I, and every time I write integral over this random measure, but it's a very specific random measure, it's a point process. Actually, this is also just the sum. So this time here, as an example, I could rewrite it as sum. Once I've sort of defined these notations, I say that's also sum over 1 to k of my sort of test function here, xi. All right. So, but that's, as I was saying, that's the general form for random measures. But because we have a very specific random measure, we can simplify this and define something that people call the Laplace functional. So because the measure we look at actually is, in particular, is positive, so I can simplify and say that this test function just basically remove the complex. Don't need it for this to be well defined. Exponential minus, sort of same thing. Sorry. Whoop. X dx. All right. And this actually is useful because if you can use it to deduce your first moment, and you can also use it to deduce higher moments. So so this one in point processes, I think we very rarely use, but it's just to make the connections with random measures. And this one is useful, but it's still a little bit complicated. And here we see that basically we have exponential sum, and we can simplify this by just assuming our phi hat is minus log phi. And so now we have so what I just said, probability, generating functional. Okay, I'm not only going to write it once. All right, and so I say, so this time I define it because I'm going to use it. H phi, that's, I mean, again, this is a sum, actually. So you can see this is just product over 1 to k of phi xi. Okay, that's a lot nicer. I can work with this. But, well, as with probability generating functions, if you want to deduce something from a probability generating function, you need to differentiate it, right? Take a derivative. So here you need something a little bit more general. So I mean, people use different notations. I think there's no set notations, but it's a so you need a functional derivative, or in this case, just also a directional derivative. For the sort of applications we look at, you can take Gateau or Fréchet, everything works. In some cases, you need something a bit different, but it's any directional derivative you want is going to work here. And so we say the derivative of h at point here is a function, phi, in direction psi, and then it's just basically this usual stuff, except we have a direction, right? Just write it for completeness. Right. That's the psi. It's not very good psi. It looks like zeta. All right. And so, but we don't need to think too much because actually everything that we're going to differentiate is going to be basically either exponential or product, and they just behave sort of normally as you would expect. So if you want to take the directional derivative of something a bit more complicated, then you need to think about it. In particular, if you have a composition and you take the directional derivative, you don't have the sort of just product between the derivative of what's inside. I mean, the usual chain rule, I'm not going to give it to you. But you actually have something more complicated. You have the derivative of the outside function taken in the direction of the derivative of the inside function. So you have things like this that are less intuitive because you're dealing with more general things. So it's just an advice. So, but here we don't need to think too hard, and in particular, this is quite nice for the problem I had here because I need to give one more thing. If I want to find the first moment of my point process x, so here I'll take it as a measure. I'll just measure a function phi. I think everyone attended at least one talk that's doing this. Yes, yeah. Just for simplicity here. Yes, so this, I just need to differentiate my, I'm going to say PGFL, otherwise it's too long. Just going to differentiate my PGFL, evaluate the function that's 1 everywhere, and in the direction of phi. That's easy enough. And so if I want to prove this little result here, just as a sort of example, to like familiarize ourselves a bit with this. So now I want to write, I should, for completeness, I guess I should put x here. I want to write the PGFR of x plus x prime. And without thinking too much, here we are the product of all points. But now we have, actually I'll write it up. Now we have x plus x prime. And that's really just the sum, for instance, 1 to k delta xi plus sum 1 to k. I introduced new notations k prime, but that's pretty clear here, I hope. X prime. So this is, I'm just forming a new point process that's just all the points together, right? And so this I can easily deduce that product 1k, yeah, so I wrote it, where is it now? That's very simple. Phi xi product I1k phi x prime I. Right? That's cool. And we just differentiate this. We want to find out the first moment of x plus x prime. Evaluate at function phi. And so, just add one line for if you've not seen it. And that's because here I have to assume that the independent is very important. If it's not independent, well, I can't do anything here. But if they are independent, then it's just PGFL of x, PGFL of x prime. And as I was telling you, for products, there's directional derivatives. They're not complicated. And so this is just take the directional derivative of the first guy. Of course, I got it wrong here. 0.1 direction phi. The other one, I leave it as it is. So at 1, because I evaluate them at 1, right? Plus, and now I differentiate the second guy. 1, phi. And well, if you look here, what happens if phi equals 1 everywhere? So the PGFL is just 1. So that's, we have product of ones, and expect that's 1. So yes, so this, as expected, is just the sum. And so this result, here again, I was really just for sort of warming ourselves up on these sort of operations. And whoop. And so these two results, actually, together, we can sort of apply dynamics to our points, and we can add some independent point process to this. Basically, we've solved prediction already. So this is a result due by Mahler. So due to Mahler, sorry. So he actually proved it in a different way, but Mahler likes to write everything with what he calls random finite sets. So he comes from sort of random set background, so I think it's natural for him, but I prefer to write things with point processes. You can read this paper and make up your mind. I invite you to do it. And so maybe write a little bit abstractly here, but I just condition on all previous observations. So that's my posterior first moment at the previous time step. So except it's the first moment, otherwise it's really nothing complicated here. And so if I want to predict this, I just add the first moment of my new target, so it would be for birth. And OK, here there's a little detail, but probability of survival times I just predict my previous targets. Right? So one very easy implementation of this sort of recursion, first moment recursion, is if you assume everything is Gaussian. So of course, for the first moment, you can't just take a Gaussian, but you can take a Gaussian mixture. And you can sort of think abstractly of each Gaussian mixture, saying, oh, that's one target around there. And then this is very easy. You just apply Kalman filter prediction to all the terms in your mixture, and you say this is also a Gaussian mixture, and add some new Gaussians to it, saying that's maybe the new targets that are coming around there. Right? That's all it's saying. So to take care of the PS, you can sort of, again, Mahler doesn't do it this way, but I like to just extend my state space S with some symmetry state. So if a target disappears, it just goes sub psi. And so we can extend our Markov kernel to this extended state space. And we just say, oh, if we were in X and we go to psi, that's probably 1 minus PS. And otherwise, if we come from X prime and we go to X, we just multiply by PS here, saying this, to take into account this sort of depth process in the dynamics. But if I just apply, the two those two results here in this slightly extended case, but I'm only look at the first moment on S, I just get this. So there's no 1 minus PS because we sort of symmetry state, we just throw it away. And we're only interested in targets that remain, so that's still within S. So it's just to say, well, you can do this quite simply. But this is the easy bit. As you can imagine, it's, as I said, it's the data association that's hard. So it's when you receive all your new observations, you have this huge combinatorics, and you need to do something about it. But the prediction is not the difficult part. But actually, with this point process formulation, the update also can be written in a very nice way. So the original proof by Mahler is based on this. Actually, first I'll go through a bit through the expression. So as before, so we have our predicted first moment given all previous observations here, and here, and we want to deduce the updated first moment with in light of the new data we received, yn, and actually we have a very simple and sort of very intuitive expression. So just to be consistent with notation, I put integral here, but again, that's just the sum of all the observations. And the first moment, we just say, well, all our targets that we had there, maybe they are not detected. So we take this into account. Or they were detected, so we have a PD term here, and detected with one of the observations. So here's some of all the observations. But because it's only one observation for each target, it's sort of competitive. And here we have, I mean, of course, this comes from Bayes' rule, but I'll show you that later. And we say, well, either this observation, so here we sum of our observation, we take observation y. We say either it comes from the target with some, the likelihood is PD times normal likelihood. Normal, it means standard likelihood, sorry. Or it comes from the false alarm or any other target. Then that's it. And you say, well, that's reasonable, right? Well, so the proof is a bit harder than that. It's just like, I'm not going to write the full details, but just to give you an idea how it looks. Right, so, okay, so I didn't, right. So I'm going to introduce some more PGFRs. So I say PGFR of the two positives, to TP, just a bit different from, well, I have to take different notations because there's specific parts of it. And so given some, what put XI? Yeah, I don't need to put XI. Given some state X, so here we want to write for one target that would be at state X, that we don't know, we just condition on that. We want to write the PGFR of the observations it produces. So if it's only one target, by our assumptions, either it produces no observation at all or it produces one observation. And so that's quite simple. And here the PGFR is just 1 minus PD plus PD integral. So I use phi tilde because we're on the observation space. So just to distinguish, y and my single object likelihood, x dy, right. So this is really just saying, oh, either we have no observation or we want one observation with this distribution, depending on 1 minus PD, PD. So we're just putting everything together in the PGFR. Then we have PGFR for the false positive, again on the observation space. This one doesn't depend on the states. We've assumed that. And so here it's just, again, it's just Poisson. So Poisson takes a very nice form. Just lambda 1 minus phi tilde y, and this va theta y dy. So bracket. So actually, if you know the PGF of Poisson process, this doesn't really come as a surprise. But now we have something that's taken the function as an argument. It's a little bit more complicated, but it's really the same idea. And so what I really want to write is my joint joint PGFL describing all state and all observations. So this guy takes two test functions, one for the state, one for the observations. And, well, I mean, you can't deduce completely, but it doesn't really come as a surprise. Basically, you have, not G. I used G in my note, and I realized I used it in the slide, so I'm changing everything to H. If you see some capital G, you tell me. All right. So that's for the observations. And again, the PGFL of the state and evaluate this at the test function of the state, and also evaluate it at the PGFL of the true positive this time. Phi tilde, given this is just a dot, ugly looking dot. Right. So, well, it's not really, it doesn't really come as a surprise, I think. So either sort of independently here you have the false positives for generating some observations, or depending on how is the state, we generate also some observations here according to the sort of true positive process. And so this is a function of the state, this is a function of the state. That's well defined. And the sort of big step, so this was sort of one big step also in Malloch's proof, and the next one that's maybe is that you can write Bayes' rule basically in the PGFL format, and you say, well, Gx. So here I've dropped some indices, and just for simplicity, I hope that's okay. Phi given my observation point process is 1, 2. Okay, here I say some realization of it. So I have some realization of my point process, delta little y, and so this. So we still have like the sort of standard form of Bayes' rule, but written for this guy, and so we need to take the differential of this. So we don't take the differential in phi. So I put 0 to say we take 0 times differential, and m times the differential with respect to that guy. H x y, and right phi tilde, right, and I take this in the direction Dirac y1, Dirac ym, and I evaluate it at phi tilde equals 0. So. And same thing, basically you just normalize this thing. Instead of taking it phi, I take it at 1. 1 is just integrating everything out. Phi tilde, and then same thing, y1, ym. Okay, sorry, that's phi. So, yeah, one property that I missed here, I should have recalled. Also, if we want to get a distribution out of this object, so for instance, if I want to know if when there's only one point in the point process, what's the distribution of that point, I also differentiate, but this time I differentiate in 0, also in some test function. So that would give me the probability of p phi for only one point here. So here we do the same thing, but for m points, and so this is sort of giving you the something that's related to the probability given those observations. Same thing here, except we integrate out the state. And if you look a bit closely here, this is an exponential. We've assumed that our state point process is also a Poisson. I should have said more clearly, that is an assumption. It's not naturally Poisson, but we assume it is Poisson. So this is also an exponential. And this is just some sort of linear functional. So actually, this time here is just one exponential of some relatively big expression, but not too bad. And then we do the recipe we had before. We just take the first derivative of this guy here with respect to phi, evaluate at 1, and we get this. That's pretty neat. So there's a little bit of cancellation and calculation I'm going to spare you, but it's the idea. And it's, yeah, I think it's something that's quite nice, and it's a pretty smart way of using those PGFL. Not quite obvious. Once you get used to the proof, you're like, okay, well, that sort of makes sense, but it's, and this is like basically just Bayes rule in a PGFL space. Oh, there's also a H. Yes?
So you get the recursion for the previous.
Yes, so then you can just iterate. So, but as I was saying, here in general, this is an approximation. In general, actually, this guy, so of course we just compute the first moment. But if we were to compute the full distribution of this point process, it wouldn't be a Poisson point process. So if you want to apply a new update after that, if you get a new data set, a new set of observations, and you want to update again, it's the fact that you assume the prior is Poisson, this is an approximation.
And what is the distribution y and dy? Does it depend on them or not?
This guy here?
Yeah, this guy.
So yeah, I guess maybe I should have written differently. This is really just a sum on the observations. So the observations they're given. No?
Oh, okay. So there's no, so it can be evaluated easily.
Yes, yeah. And again, you can do a Gaussian mixture implementation of this, and this is one of the most popular implementations in practice. I mean, at least if the dynamics observation are reasonably well approximated by linear Gaussian. So, so this is basically so if this is a Gaussian mixture, then you can get this term inside, and you have this sort of numerator of Bayes rule, and so you do some Kalman filter, but you get the marginal likelihood, which is the important bit, and the marginal likelihood tells you basically how likely is this association between this observation and the sort of this Gaussian term. So there's another proof. I'm not going to give a lot of details about it because actually taking a bit longer than I thought. But using the same sort of tricks, and that's a proof that is proposed by Pierre Dalmoral a bit later, and he was really trying to understand this sort of recursions, but he is not so familiar with the PGFL approach. And it's true that you do all the operation in a sort of different space. So yes, you get the right result, but you don't really get the intuition of what's going on. And so you can do the same sort of tricks by also augmenting the observation space with, this is the empty observation. So if a target is not detected, it goes to phi. This observation is phi. And so in the same way as before, we just augment also the likelihood for a single object, saying, well, if the object was at x, was the probability that is misdetected is 1 minus PD, right? So everywhere, actually, in general, you can make PD depend on x by just didn't for simplicity. And so this is really the steps. Again, you can sort of consider this as a picture. So this is just the Bayes rule written in Pierre's notation with the likelihood, this likelihood and this sort of prior. So here this is first moment. So here basically the idea is to say, well, if we given all the observations, so if we actually know how many targets are misdetected, so how many targets we don't see, so at first we're cheating a little bit, and then it's quite easy. We just give all the actual observations to, well, we just sort of update our first moment with this, and we know how many also are not detected, and so we do exactly the same thing with this time misdetection. So it's just the idea. Again, it takes some time to understand the expression, so that's not necessary. And so this yn is really, I just basically augmented my true observations with, I'm cheating here, I'm saying actually I know how many targets are not detected. But if you do it in 2 steps, so this step, it's relatively easy to understand, but of course, as I was saying, we're cheating a bit here. But now we can say, actually, the expectation of this extended point process, given the true observations this time, actually that's also simple. There's just Poisson. it depends on the first moment, but this is really just Poisson, and we're saying, well, I take the true observation, I add k misdetection, and that's it. So with some Poisson probability. That's really the only thing it's saying. And then you just use the law of total expectation, combine those two things, and use the trick that, so here, this functional is really taking the whole point process as a function. Here we allow ourselves to get the probability, the full probability of the process. But if you change it for this way, so you say actually rather than allowing anything to be done to xn, or just evaluate the function f at the points of xn, then this expectation just gives you the first moment. So this is the steps, and I think it's interesting to see that you can also do it without going through the PGFL technique, without going through this sort of transformation. It might look a bit more technical, but you can do it, and you see it's important for later. So I gave a little spoiler. Of course, we can do this Gaussian mixture implementations, and they were so Barnouveau, who talked during the opening workshop, so he proposed these Gaussian mixture implementations, and he also proposed actually a bit earlier of course, sort of particle filter implementation, the SMC version, with Sumit and Arnaud, when they were all in Melbourne at that time. So the thing is, if you do a particle filter implementation, which of course is quite natural, if you have nonlinear dynamics and nonlinear observations, well, you cannot go anywhere with your Gaussian mixture. So, but you have, well, the first thing you would do is basically approximate the whole first moment with one particle filter, with one. And so the problem is that doesn't tell you where are the targets. You have to run some clustering to realize, oh, I have more mass here. Or more mass there, and you have to sort of try to understand where are your targets. I mean, you just have basically one SMC implementation, and the problem is this it actually brings in a lot of errors, and it's also quite time consuming. So it sort of destroys it a bit, but you can also sort of try to cluster it automatically. Just identifying which particle have been updated with which observation, something like this. And you can rewrite things. So again, that was proposed by Pierre. And in this case, you can just run one particle filter per target. So that sort of solves the problem. It can be more computationally demanding, but at least you don't lose a lot of performance by doing some clustering steps. So for the Gaussian mixture case, so I mean, we have to handle the Gaussian mixture, although here, actually what's very important here is that I turned this sum of a permutation we had before. Now it's just a sum of observations. So the complexity here is much smaller than if we were solving the full problem. So people usually say this the whole method is linear in the number of observations and linear in the number of targets. So that's basically the smallest you can do. You still have to evaluate at least individually each target with each observation. Otherwise, if you gain on this, basically, so it has to be a heuristic. So yes. So but in spite of this, although it's only linear, I mean, if you have a lot of observations, a lot of targets, you would actually increase the number of time in your mixture still extremely fast. And so you have to use some pruning, deleting the terms that are very small. So these techniques are independent, have been independently developed for Gaussian mixtures, of course, and merging, which is just basically merging together terms that are deemed closed, depending on some distance. It can be Mahalanobis or Hellinger or some others, whichever distance you like between Gaussians. And so I would say the only thing, this works pretty well. The only thing is you could think, oh, I'm just going to do much less merging and it's going to be more accurate. And that's true, but because you just have this Gaussian mixture and you still need to extract targets. You need to say, if you want to have some estimate, you need to say, well, this Gaussian term, maybe its weight is high enough is likely to correspond to the target. This Gaussian term maybe is very low weight, and I'm not going to say there's a target here. I'm not sure enough yet. But this simple way of extracting targets, which is basically what everyone does, it really depends on merging, because of course if you have a lot of Gaussians that are like basically stacked on each other, you look at the individual weights, they can be all small, well actually they form one sort of big, well non-Gaussian but nearly Gaussian term, and so the merging is really important here. You can't, if you don't do it, or if you do it for very small tolerance, then you would also have to do some clustering, which sort of defeat the purpose. Okay, so going back to our simple scenario. So again, we have our state observations in orange and the false positive in green, and that's the first moment. So here, I just compute. So this is still a Gaussian mixture, but I just evaluated at all points, and we can see it's doing. It's not an easy problem actually, because the noise here is quite high. So and we can see it's easy to sort of get lost, as I was showing earlier. But it's still capturing actually most of it, and that's pretty good. If now I run this track extraction, and for instance, I think in this case, I display the mean of all the Gaussians that have weight more than 0.75, for instance, 0.9, 0.5, you can do whatever. Here's 0.75. Well, we still track those things most of the time, right? Well, here we're losing this one, but here it's a bit hard. But this is doing relatively well. But as I was saying before, you don't, with this sort of things, you don't identify who's coming from where. So you've lost identifiability. If you're asking, oh, is this object here? I'm pretty sure there's an object here. Where it comes from, well, maybe you can deduce at the beginning, but then you don't know, right? So you lose by killing the combinatorics, which is a good thing. You lose some information, and if that information is important to you, well, you can't use this sort of technique, or you have to apply some post-processing, try to recover it. Right. So just to so this is the sort of whole codes. So it's very simple to implement. I mean, as you could tell from sort of the equations. Here I've basically assumed that you don't have to look in the details. It's just to show you that it's quite simple. But here I have assumed that I have some class here that takes care of my Gaussian mixture. So there's no the pruning and the merging can be a bit long, but I think that's independent of this sort of recursion. So I mean, the code would probably be as long or longer, but the sort of core of the algorithm is very simple, it's very easy to implement, and I think it's also part of the reason why this has been very successful. So just a quick word about, of course, the reason Pierre was interested in these things, he wanted to analyze it. So I'm not going to go into a lot of details about this, but just to give you some ideas. Here we rewrite the whole recursion. So first, this sort of indices just say that's, for instance, this term is at time n+1 given all observations up to time n. So it's usual in some domains, but not less usual in some others. So here, instead of propagating the first moment, we have a normalized version, eta, and the total mass. So of course, from those two terms, we can recover, just multiplying, we can recover the first moment, but it happens that it's actually easier to do the analysis in this form. And this operator here is just prediction and update together, right? And so as usual, we can rewrite this as a semigroup transformation. And so we actually separate them. Either we look at the evolution of the mass, or we look at the evolution of the probability measure here. And to do the analysis, we have to look at the sort of composition of those operators over several time steps, although you cannot say anything. So here it's actually quite simple. There's some Lipschitz type assumptions. So we assume that those transformations here for the mass they are Lipschitz with this constant. And so the constants have some forms. I've given them here, but I mean, you can look at the paper for the details. Huh? Actually, there's the book, but you can find it easily. And it's the same thing for the measures. So here is a slightly more complicated type of Lipschitz assumptions, but also have the constant. And this is for each n prime and mu prime. This is a Markov kernel on the space of measurable functions with oscillation 1. This is the sort of usual objects. And so there's also, so that's the Lipschitz assumption. We also have a continuity assumption here. That's of the similar type, but I mean, similar form. So you would say, well, okay, these assumptions, maybe they're not very intuitive, but we'll see actually later we can do something with them. And under these assumptions, you can prove some sort of exponential stability. And well, in the theorem, Pierre gives all the constants and everything, but I didn't think it was necessary to replicate them here. But what's interesting is we've just assuming that we have some lower bound and upper bound for the likelihoods. Then for the first moment recursion, we've just written. Basically, if we assume that the probability of detection is high enough, is more than some constant, and if the number of birth actually is expected number of birth is also high enough, but the false alarm not too high, then basically those assumptions that were complicated, they're verified. So I think that's quite neat. It's interesting. It's not a very quantifiable result, but it says that under those assumptions, so your first moment recursion is going to be exponentially stable, and so it's I think probability of detection is high enough. That's quite natural because you say, well, I want to see my targets, right? To go to have stability. I don't want too many false alarms. Maybe the less intuitive one actually is the lower bound on the birth, and the reason is that you want basically new objects to appear often enough that even if you make mistake, you're going to forget them. They're going to disappear. New objects are going to get in. Well, if you have no death, no birth, then you're sort of fixed. And if you make a mistake, then maybe you won't recover from it. So it needs to be sort of dynamic enough in the number of objects to get the stability. And yeah, that's what I'm saying here. Okay, so one of the main criticism of this is that it has a short memory. So for instance, I mean, I'm not going to write any equations, and it's just if you, so people find it very intuitive, but then they expect more than what it can give. And so if you start, that's like time, let's say for instance time 1, and you initialize with just, let's say, one Gaussian with weight 1. So it's a Gaussian mixture, a single term, and only weight 1, right? So the expected number of target is 1. That's not complicated. But for instance, here you have no false alarm. You see the target all the time, but you have 2 observations here, and you apply the recursion. You see that at time t equal 2, then you're going to get actually two Gaussians like this. I mean, if you don't do Gaussian mixture, it's the same. And this, let's say W1 is going to be almost 1, and W2 is going to be almost 2. And so here we said we initialize, we say, no, there's 1 target. There's no birth, no death, no nothing. And second time step, it tells you expected number of targets 2. So that's what happens if you don't do the combinatorics. There's only so much you can tell. And so the sort of just summing the first moment over the whole state space to get an estimated number of targets, actually people don't do it because they realize quickly that doesn't give you the information you want. So I think it's just a word of caution to say, well, it works well, it's very simple, it's very fast, people like it, but you have to be careful with sort of things. And so this I said. So Mahler actually, to sort of address those criticism, he proposed to say, well, we're going to remove the Poisson assumption, which is the sort of central one, and just assume it's an IID point process. So in space, if you have n objects, there's still the product of n distributions. So it's still RID in the number of objects, but RID in space, but here you assume that the distribution on the number of objects can be anything. So you model the whole thing. So that's good because this doesn't happen. If you say, I know for sure there's one target at the second time step, you also know for sure there's one target because you propagate the information. But you actually also has some disadvantages. I'm not going to go through it too much because I'm actually running a bit out of time. And so Vo actually, since about 2014, he also suggested to use, for the question of indistinguishability, suggested to use marked point processes. And I think that's sort of natural thing to do if you, starting from point processes, you say, well, I'm going to each object, I give just one label, for instance, numbers 1 and n, that's unique to the object, so you sort of re-identify it. So of course here you also take the whole complexity, so you have to deal with it, as he was explaining in his talk, but he's showing that now is the sort of things we can do. But I also have been working on some other things in my thesis. I'm not going to talk a lot about it. Just so I sort of started from scratch and try to have some representations where we have partial distinguishability. So we say some things we're not able to distinguish, for instance, things we've not seen yet, and some other things we know. We've seen them and we know they're there, and we can, for instance, know their trajectory and everything. So it's quite a lot of work, but I think what's interesting is that if you, in the case where, again, all targets are independent, the sort of usual assumptions, what you get is a point process, but on space of probability measures. So you, instead of saying there's one point at this state, you say, oh, there's one target with this distribution, or one target with this distribution, et cetera, et cetera. So I'm not going to go through it, but I find it interesting that you sort of come back to point processes, but on different space. So this, okay, is giving good results. Since we look at the first moment, you can also look at higher moments. You can look at the variance and try, for instance, if you have a sensor scheduling task and you want to see, oh, where should I point my sensor? Well, you can say, I want to point my sensor in areas where the variance is high because I want to know what's there. So it's nice that we can also derive those things and study them. Okay, there's other techniques. All right, so this is my last slide for this part. So I think one of the fundamental problems with all algorithm, any of the algorithm I've talked about, is that well, in practice we don't know the distribution of the false alarms. We don't even, I mean, it's not even clear that from one step to the other it's going to be any similar, and so there's really, we basically know nothing about it. We don't even know that it has some regularity. So even if you parameterize it, you have in some cases it's almost impossible to learn the parameters. Also, there's often we have absolutely just no idea where the objects come from. So what people do is they just, when there's an observation, they say, oh, this observation, maybe it's a new object. But actually to sort of formalize this is not so easy. And this is actually to give you some idea also for the probability of detection. So this is what people call a radar cross-section. And that's to show you that at least as some range. So if you're close enough, that's basically the sort of, if you send for instance, radar, if you have a radar in this direction, that is here, is looking in this direction, depending on how high is the signal, that's related to your chance of seeing the target. So if you're very close, then actually you're sure to see it all the time. If you're very far, you never see it. But in between, depending on very slight modifications of the sort of position of the object, the probability of detection can vary very dramatically. And so in practice, just saying, well, it's probabilistic with PD, for instance, 0.9, that's an ID that's very unrealistic. So there's some of the challenges, and even if that works, you can say, well, I have some modeling that's just like sort of not too restrictive, and I still get an answer from my algorithm. In terms of uncertainty quantification, I mean, if everything is different from what you modeled, you can wonder if that means anything. Okay, so that's the end of the first part.